Okay, let's start it. We're going to talk about three-way factorial design. And when we have three-way factorial design, in reality, what we really can consider is that you have two-way factorial design linked together. So in other words, is that if I'm using high, medium, low, as x3, x2, x1, then you know that from x1 to x2, there is a jump if it's a positive effect. x2 to x3, there is a jump, there is a positive effect. So now x1 and x2 to x2 to x3, there are two velocity, right? It's the x2 minus x1 and x3 minus x2. So you can consider this. Okay? If I have something, okay, I have low level, say x0, or medium level and high level, and let's just call them -1, 0, and 1. Okay? So I know that from -1 to 0, what is the increment? 1, right? From 0 to 1, the increment is 1. So if I said that the effect is something like this, 3, so this is x, okay, or x1. This is x and this is y. And then the y effect, if I said is from 3 to 6 to 11. Okay? So what will be the velocity? Is this guy minus this guy divided by how much time increment? The time increment is from -1 to 0. So really just 3. That's the velocity. Agree? And then of course I can use the same tricks. Control C, Control V. Then that's the 6 to 11 is the increment by 0 to 1. So it's still jumped by 1, right? So now I have two linear effect. Okay? Then I would like to figure out if I call this is my velocity. Okay? I would like to figure out my acceleration, right? So the acceleration should be what? In reality is the change of velocity. So it should be this guy minus this guy. And divided by the rate of change. Okay? So now, well, let me first figure out, so what is the rate of change? Okay? One way to figure that out is, so I have a differences here and I have a differences here. So I can consider that the total differences can be considered is beginning plus the end minus 2 times the middle part. That'll give me exactly the 2. Okay? But conceptually, they are saying what? Well, people pay attention here, okay? Here I'm talking about, what is acceleration? It's the rate of change of velocity, right? So the rate of change of the velocity in reality can be considered as what? Okay, if the beginning, well, watch here. If the beginning minus the end, plus the end, minus 2 in the middle, okay? low, high, minus 2 in the middle. If the 2 in the middle is exactly the average of the beginning and the end, then what will be the acceleration? Nothing, right? Well, here, let me try it. Okay, so 11, we'll put it this way, 3 plus 11. 3 at the beginning, 11 at the end. So what's the average should be in between? 7. So let's see, if I put 7 in, what will happen to the acceleration? Let me put a 7 in, what will happen to the acceleration? Nada, right? And of course, if the middle I put 5, something wrong. Oh, yeah. Yeah, okay. Let me use even smaller. Let me say use 3. Okay? Then you will have no velocity, and boom, run to 11. But I think the most easy way to think about what is acceleration or the nonlinear part really is what? It's if I'm having 7, then see the velocity are equal, so there's no velocity change, right? So it's linear, then there's no acceleration, or from here to here, from here to here, there's no the middle part is right in the average between the two. So if this is the case, okay, do I really need to investigate the acceleration? If there's no acceleration effect, no need. Follow me? Okay, so actually, I don't know how much physics you guys have. There are names for the finite differences. Displacement differences is called velocity, right? Velocity differences is called acceleration. What's the name of acceleration differences? It's called jerk, jerky movement, right? So why you get car sick? Accelerate, decelerate, accelerate, decelerate. Jerk, and then what's the name after that? Snap, pop, and crackle. Okay? Go Google after class. There are actually names for each one of them. And why this is important? For those of you like to do the supply chain management, they talk about supply chain, they always talk about what? Bullwhip effect, right? And what's bullwhip effect? It's the snap. Okay? Okay. So here I'm talking about that in a less intuitive way. Linear effect is 2 minus 1, 3 minus 2, velocity, velocity. And then the linear effect become the 3 very high minus very low. Or in y, because the two cancel out each other. And then what is the quadratic effect? The quadratic effect really is the acceleration effect. It's the rate of change of velocity. And so it's 3, beginning minus the end, minus 2, beginning plus the end, 3 plus 2 minus 2 in the middle. Okay? And you can write it in a vector form, like this. Okay? Everybody on the same page? Okay? Looks simple, but you can get confused really quick. Okay, now what if I have 2 factor? Before, if I have 2 factor in a 2 by 2 fashion, is what? High, high, low, low, high, low, low, high. Now I still have the 4 corner, low, low, high, high, low, high, high, low. But I also have this cross. Those cross basically is what? Is if you have 0, 1, 2, 0, 1, 2, 0, 1, 2, you have 0, 1, 2, 0, 1, 2, 0, 1, 2. the combination will give you all those points. Okay? And with all those points, now rather than using 4 points to decide, are they parallel or not parallel? Parallel, no interaction. Not parallel, there is a crossing effect. Now we're using 9 points. So we need to develop a 9 point, just like before. We have a contrast square. We need to have the sum of square total, everything's, okay? Now, we're doing the same things here. Factor A, low, medium, high. Factor 2, low, medium, high. 0, 1, 2, 0, 1, 2. Okay? And then for each one of them, if I have only one observation, 1, 0, 2, 2, negative 1, 2, 0, 4, 1, 1, negative 2, 3, you still can build your ANOVA table through this kind of spreadsheet. Okay? And how? I have the spreadsheet right next to it, and I already give you the PowerPoint and the Excel file. Okay? And how are you going to use those terms to build? People think about it. A got linear effect and quadratic effect, right? So that's 2 degrees of freedom. B got linear effect and quadratic effect, 2 degrees of freedom. So, but totally I have 9 observations. I have 9 degrees of freedom, minus the overall average where the central station going to be. I should have 8 more degrees of freedom, 4 more degrees of freedom I can use. You agree with me? 9 observation, 9 degrees of freedom. A linear, A quadratic, B linear, B quadratics. Where are the other 4 degrees of freedom going to be used? Since we have high-low, or linear, quadratic, now we will have the so-called linear effect, linear quadratic effect, quadratic linear effect, and quadratic effect. Okay? And one way to think about this is what is a linear quadratic effect? Okay? Well, linear, I don't need to talk about it. Just like what we had before, the parallel things. Quadratics is this, okay? If the geometry look like a ridge, okay? And yeah, so it's kind of like, okay, I only have the roof line this way. Go up, coming down, go up, coming down. Okay, so this could be A low, A medium, A high. That's it. So linear quadratics. Okay? And then, of course, I can also have the other one is saying, hey, B is doing this linear quadratic and nothing going on. Okay? Now people, what will be the nightmare is the response surface that we're going to investigate later is if I have the quadratics, okay, there are basically how many different conditions we can explain a quadratic effect. Let me put it this way. The landscape can be convex. Convex means what? Holding water, right? So it's like a baseball or like a bowl. Okay? And this is convex. Okay? That's both A and B, or both x1, x2. They are basically saying what? I will have the lowest points in the middle. But A go up, A go low. Okay, so no matter in this direction or in the other directions, it's always low, medium, high. Low, medium, high. It's right in the middle. Okay? So if I'm talking about this is what? In the middle, I have the lowest point. The four corner or the other. You guys can you guys see this? I have nine points, right? Here. I have 9 points. 0, 2, 0, 1. Where is the lowest point? At 1, 1. Follow me? If 1, 1 is the lowest point, everything else is going up, then it's like holding a baseball cap upside down or a bowl holding water. Agree? And then of course, if I turn it around and say concave, that means what? You have a maximum. 1, 1 is the highest point. Okay, those two are actually not too scary. There's one more, very, very scary one. What's that one? Saddle point. And what is saddle point? Saddle point means that could be max, could be mean in the middle, depends on how you look at it. So yeah, this is a saddle point. Look at the saddle point. If I'm going this directions, high, medium, low. The medium is the lowest point, right? But if you look at it from this dimension, high, medium, low, -1, 0, 1, it turned out to be what? Lowest points, highest points, lowest point. So in other words, is that before it's either convex or concave. Both say convex and concave. Both a bow or bow upside down. This one is depends on who you're talking about. Okay, and right now I'm just giving you the thinking process involved. So before I go any further, couple of things. Conceptually, you got it, right? Wiggle your finger if you said that I got stuck. We have velocity, and velocity change, which is acceleration for the quadratic effect and linear effect. Everybody agree with me? Everybody sees that jump and jump. If the jump and jump follow the same slope, linear. But if accelerate more, or accelerate less, then there's a nonlinear effect. Or decelerate more. Okay, basically the velocity is not a constant. If the velocity is a constant, then your quadratic effect disappears. Second, you have 9 data points, okay, or 9 category for computation, minus the overall average. Use 1 degree of freedom. You have 8 degrees of freedom. That 8 degrees of freedom, I can use that to represent linear, quadratic for A, linear, quadratic for B, and linear, quadratic, linear. So there are total 8 degrees of freedom. Second, if you have 8 degrees of freedom, you can use those 8 degrees of freedom to look at the landscape in such a way that intuitively could be convex, could be concave, convex happen at the same time. Okay? And why it will happen at the same time if there's a saddle point. Okay, so now let's do the computation. And here is the spreadsheet I give you. Okay, and for this, first, linear quadratics. Okay, linear quadratics. Okay, linear. Okay, so everybody sees that if I only have B column and D column, I have what? -1, -1, And then I have the 0 in the middle. If I ignore all the 0, then this section disappear. This section disappear. So if you only look at linear change, totally how many data points you need? Only 4, right? Only this one and this one. And then quadratic. People think about it. This minus this is 1. This minus this is 1. So you can consider this minus this and this minus this is what? 1, negative 2, 1. Because negative 2, 1, what's the beauty of it? That is when you sum this together, the total should be what? Well, it should be a contrast, right? So that will be that contrast. 0. So we'll build a contrast. And next, I'll do that later. So here, pay attention is now I have the quadratics. Pop in the middle, pop in the middle, pop in the middle. And of course, once you have the linear and quadratics done, everybody see that how I build a linear and quadratic contrast? Yeah? Okay. And next, multiplication. Linear times linear is linear. Linear, quadratic, or done. Okay? And then, of course, at the end, this is your night observation. Okay? And let's do some checking here. Okay? If you sum any effect here is 0. People see that they are 0, so they are contrasts, right? Next is are they orthogonal contrasts? We should have 2 vector. The dot of the 2 vectors should be 0. So if I do a sum product, okay, I'm lazy. Just try a few. Okay. Everybody see that? The sum product is also 0. So agree with me. This is a contrast, also a orthogonal contrast. But this orthogonal contrast serves all the things I'm talking about. The velocity change, the linear, quadratic. And later on, okay, when we do response surface, we will play the tricks, build a cage, put the center points. And then at the end, we'll just stretch out a little bit and to build the whole things. Okay, next, all you need to do is stop doing the sum of square of each one of them and the sum of the this times this. I know before what I did is I copy this and then basically create another column, right? Saying what is AL times Y, AQ times Y, and then do the sum. This time I'm just lazy. Directly have a sum product of each one of them, of your performance measurement times the contrast you build. And then you get your contrast value. And then what will be your sum of square? And just, your, well, I missed one. How did that happen? I don't know. Okay, so I have, this is the sum of square for each one of them. Okay? And here, people, look at A effect. Quadratic is strong, right? Right? Big, right? How big is big enough is 1 degrees of freedom right now. So just we can look at it directly. And B quadratic effect is strong. Okay? And usually this is the case, okay? Remember when we talk about the 2x2 or 2 factorial design, I always said that, hey, if you want to talk about A-B interactions, you better have your A main effect and B main effect, then A-B interact, right? Because priority-wise. So if I want to talk about A-B-C interaction, I need to have A strong, B strong, C strong. So it's kind of hierarchically, you start from the main effects and go on. And in this, there are similar kind of argument, okay? It's very hard for you to say that, hey, A quadratic effect is not strong, B quadratic effect is not strong, but A, B quadratic together is strong. What I'm saying is this. People, who's wearing a baseball cap? Yeah, well, I cannot show it on screen. Well, can I borrow yours? Just 1 second. I promise I won't ruin it. Okay, thank you. Here. If, let's say that we're talking about convex, I'm looking at it from the front. You see that there's a curve, right? And then you look at from the side, this view, you also see a curve, right? So here there's a curve, here there's a curve. So overall, there is a quadratic makes sense, right? How could it happen if I said that, A quadratic, B quadratic is there, but you only can see quadratic on one side, you don't see quadratic on the other side? That doesn't make sense, right? Because what will be the only situations that I can have one side quadratic? If I only have a piece of paper, I'm just rolled a piece of paper like a gutter, then you only have one side view. But if you only have one side gutter view, you have quadratic on the side, you're still not going to have a 2x2 effect. You guys agree with me? Can you see that? Yeah. I try to break it down. You should intuitively consider that. It doesn't make sense, that's why a lot of time when I sit in somebody's defense for their dissertation or thesis, they start talking about those high-level yada yada. I'm kind of like, slow down. I don't want to hear the high-level stuff. Give me the basic. Break it down. If I don't see the main effect, you start talking about a three-way, four-way. Thank you. That's a science fiction. Okay? Okay, so once I build that, okay, you have the Excel. Then you can break them into the sum of square. And then people look at here. The main effect, okay, I will have the 5.78. Okay, 5.778. Where's the A coming from? I'm sorry, the main effect, A, I have a 4.22. Where the 4.22 coming from? Linear plus quadratic, right? 1.5 plus 4.72. That'll give you 4.22. Where is the B effect coming from? Linear plus quadratics, 0.17 plus 1.39. Okay, so you can look at them as 2 degrees of freedom, linear quadratic, 2 degrees of freedom, linear quadratic, and then all this first 4 add together, 4.22 plus 1.556, you got your 5.778. That 4 degrees of freedom is called main effect, sum of square. See that? And then, of course, you will have the two-way interactions, and the two-way interaction, just the rest, okay, combined together. And you know that the monster is the one hidden in the back, is that 21.78. Okay? And that's your 4 degrees of freedom. And of course, in this example, I don't have any left for the error term. And then, of course, we need to eliminate a few terms to be used. But in this example, I don't want to do any polling. I just want you to at least using this simple example to figure out where the linear effect, where the quadratic effect coming from. Okay, so if you agree with me, Next, we could do the plotting. Symmetrics, parallel means there is no interactions for linear quadratics. And then whenever quadratic linear or linear quadratic, same things. Parallel, no interactions. Not parallel, there are interactions. Okay? So those are the 4 degrees of freedom used to describe the linear effect and the quadratic effect. Okay? Next. Okay? Sometimes this is beyond the scope of what I'm saying is you're not going to use this much in your class or your term project. But if you go for a graduate school, we have the so-called I sum of square and J of sum of square. Basically, just have the main diagonal measurement. So if I go for the main diagonal of that 9 degrees of freedom, is 1 plus 4 plus 2, that's 7. 2 plus 1 plus 2 is 1 square. So I can go main diagonal, figure out the sum of square is main diagonal sum of square, and then I can go subdiagonal, have a subdiagonal sum of square. And if you combine the main diagonal and subdiagonal sum of square together, you still partition the total sum of square 23.11 of all the effects. 8 degrees of freedom we can have. Okay? And while we're doing this, that's beyond the scope of this class. Okay? But, if you go for grad school, for more advanced evaluations, we're going to do that. Okay, now we know that if I only have 9 observations, I don't have anything left for the error term. So what do? Add more observation. So I double my observation. Now I have 2 observations per cell. So for volume, I have low, medium, high. For time, I have short, medium, long. So totally, I have double. Okay, so what? I have 18 degrees of freedom minus 1, I have 17. 17 degrees of freedom, use it for linear, quadratic, use 8. I still have what? 17 minus 8, I still have 9 degrees of freedom left. So here is the way to do the computation. And again, I made up the Excel spreadsheet. Okay. And, what did I do? Okay, you have the observation, and then one way you can think about it, okay, is you can treat them as what? Three subway station, short, medium, high, and then figure out their average and treat them like a factorial design. Not factorial design, like a simple experiment. 6 observations for 3 subway stations, right? People agree? Can I treat the experiment this way? Short, medium, high, and short, short, medium, long. 3 treatment this way. And can I figure out the subway station, the error terms, yada, yada, right? And of course, I can do it vertically, and then I can calculate the overall average. And so at the end, okay, I can treat it, what I'm trying to say is, I can go that way, I can go vertically, okay? So now I have the average of this cell, average of this cell, average of this cell, okay? And then for each one of them, I can go the total this way and figure out the average this way. So in other words, is that when I'm done, depends on you look at 6 degrees of freedom this way or 6 degrees of freedom for three subway station for short, medium, and long, or 3 subway station vertically, then you can figure out the total sum of square. Okay? And hold on 1 second. Yeah, let me do this. People show hands. If I don't do anything, okay? Can I treat this as 3 subway station, low, medium, high, and figure out the total sum of square and the error term this way, vertically? You can do that, agree? Can I treat them this way? 3 degrees of freedom, agree? Right? Then one more. Can I treat them as 9 subway station? Every subway station, how many commuters in that subway station? 2. And then you can figure out the total sum of squares that way, right? So at the end, okay, you can have the total sum of square, build it up based on that approach, and figure out the sum of square. And you can compare that old approach with this approach, okay? This is the one I just introduced, right? The contrast way. So now I do the same things. Linear, 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 linear. And I don't even need to do this 2, because this 2 in the middle here is all 0, right? So I have my 4 corner, and then I have the one in the middle. And then I build my quadratics, and then I build my linear quadratic, this way. Okay? And this is the contrast approach. So at least, okay, you know that you can do this using the central station, subway station, figure out, partition the ANOVA table. You can use the contrast way to build a contrast, to build the ANOVA table. What is the way that we had before, and I'm not doing it here, the regression way, right? Yeah. And why? Because too much work. I have one. I can, if you guys want entertaining, I can show it to you, but I probably will use SAS to do the higher level one. But here I have my 16 observation. My 18 observation. Sum it up together, and then build your contrast, build your sum of square. Okay? And when you finish your sum of square, remember the main effect for A is the sum of linear plus quadratics, and all 4 build this, okay? And this will partition and get the sum of square, not using the central station approach, subway station approach, but using the contrast approach. And then finally, whatever you've done, you can have this table done, okay? I did not put this in for your homework, but if you have time, well, I also don't want to just keep asking for homework, but I would say that you already have the answer, okay? And you should be able to do the ANOVA table by 2 different approaches. And later on, if we have time, I'll show you how to do it using the regression approach. But otherwise, I'll just give you the SAS code, okay? Show hand. Everybody got SAS access now, right? Good. Yeah. Okay. So once you do that, okay, what will be the next one? Before is 2 by 2, 2 by 2 by 2, 2 by 2 by 2. Now we just need to do 3 by 3, 3 by 3 by 3 by 3. Okay? And technically speaking, can I do some 2 by 2, some 3 by 3? Can I have A effect is 2 level, high and low, B effect is high and low, but C effect is high, medium, low, medium, and high? Can I do that? When you think you'll run an experiment with some 2-way factorial combined with some 3-way factorial. Anybody? You? Can I have a experimental design with A effects 2-way, B effects 2-way, but C effect and D effect is 3-way? We already talked about a lot of 2-way. Now we start getting 3-way. Can I do some 2-way combined with some 3-way?
Probably. I think
Why you do that?
I'm not really sure if it's how much you can get. I don't know. Because you have 2 effects and you have 3 effects. You can test how the 2 effects work with the 3 effects. I feel like I'm not random, but.
Okay. 3 ladies sitting in the back. Anything from Google? Can we do a 2 combined with 3?
I agree with what Calvin said.
What Calvin said?
That he thinks that you can, that it makes sense what you put, but not sure if you can.
And why we want to do it? Because we can. Experimental design. Your boss need to give you money and resources to do it, right? And so, do you think that you should always ask for 3 by 3 by 3 by 3?
No.
Why not? It's your life, right? You don't want to waste your time. And so when you want to do it, unless you think that there are some quadratic effect you need to investigate. So if it's A effect and B effect, you know for sure it's linear all the way. Why bother? So in other words, is that if I can have an A effect is 2-way, B effect is 3-way, what that really means is what? The configuration, no matter what, will look like a gutter. And if it look like a gutter, I know I have enough knowledge to know that there's no need to investigate everything in 3-way, then why bother? Because it saves time and money. Okay? And then, of course, you will say that what if the landscape is very, very complex? a lot of convex, concave. You got a very, very complex surface to investigate. Then we get into the response surface. We need to divide and conquer area by area. But no matter how many area we need to investigate, when I reduce that to the minimum, okay, what is the minimum shape of any things? Convex, concave, and saddle points, okay? If you disagree with me, you say there is something else, okay? I would like to see that. Anyway, now if I have 3, the nightmare become linear, quadratic, linear, quadratic, 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 linear, quadratic, you know. So you can say that there are A effect, B effect, AB interaction, AC interaction, BC interaction in 2-way, in 3-way, and totally there will be 26 degrees of freedom rather than 8. Okay? And another way you can think about it is this way. 3 by 3 by 3. How many? 27, right? 27 minus 1, 26. Here's the breakdown of the 26. Okay. So here is the experimental conditions I show you. And this time you need to do the same things and calculate a linear, quadratic, quadratics, and get everything's done this way. Okay? Okay. And the reason I did not give you a homework like this is it can be done if I give you the Excel. But guess what really the torture about? This detail. Step 1, step 2, step 3. You know, doesn't really, what I'm saying is that some of the torture we have before, it's important because I need you to visualize what is sum of square, what's the partition of sum of square. But once we reach this level of, you know, break it down more, 3 by 3 by 3, I'll say, you know, play with it, and then later on we rely on SAS to do the computation for us. Okay? However, okay, in the exam, okay, if I ask you something about 3-way factorial, probably it's more about why we're doing this. Less to do with the computation, because, you know, if you made a mistake in a computation and get panics, that doesn't do any good. But you need to understand why we're doing it. Okay? Here I'm just saying, oh, linear, quadratic, quadratic, quadratic. But in real life, that's a lot of computation. Okay. Now I finish everything for 2-way and 3-way. Now we're going to come back to some very, very simple stuff. Okay? The stuff that in our lecture 1 is called multiple comparison. And the things I would like you to put it down is, in the old days, my lecture note, I put multiple comparison right after the subway station analogy. But now I'm kind of like, well, we can do multiple comparison for single treatment, for blocking, for factorial design. Like the last one we have, I can have what? Low, medium, high for A, low, medium, high for B. So totally how many different treatment if everything's under multiple comparison? 9, right? Because 9 different comparison, remember what I just said? If the 1 in the middle, 0, 0, 1, 1 is the max, or 1, 1 is the mean, that means that that's the highest point, how much higher than the others. And that basically is a comparison of how high is high enough, how low is low enough, how much jump is too much jump. So to do multiple comparison, okay, it's not just for single treatment. It could be used for factorial design, two-way factorial design, three-way factorial design, for any combinations. Okay, so that's number one. Number two, I would like to explain to you the following. Okay, if we're going to do where is it? Oh. If we want to do multiple comparison, the most important thing is, hey, if I give you something and say which one is the biggest one, which one is the smallest one for comparison, put that down, okay? You don't do that unless your ANOVA table shows that there are significant differences. So in other words, if I say A effect is significant, okay? So if A effect is significant, compare A low, A medium, A high, makes sense, right? If I say A effect is not significant, they're all the same, would you need to do multiple comparison? No. Same thing for B effect. And then if I said that, oh, we need to do A medium, high, treat them as 9 different conditions, when you would need to treat them as 9 different conditions. Both A effect, linear quadratic, B effect, linear quadratic, A effect, B effects, their combination are significant. Then you do multiple comparison. You guys follow me? If the ANOVA table says that, hey, I cannot tell the difference between the two, and you run multiple comparison, okay? If I give you something, and at the end, you did not see any differences, and in the exam, it could have this kind of tricky situation. I say, hey, perform a multiple comparison. And then you just plug and play the multiple comparison, even though you know that there's no significant difference. ANOVA table says there's no difference between the two, and you do that, you will, even your computation is correct, your logic is totally wrong. Then you will get into, you're not gonna, you get 0 on that part. You guys follow me? Multiple comparison only need to be done when there are significant differences among them. And also, there are several assumptions I need to check. All those assumptions for you guys, if you're gonna use experimental design in your senior projects or your capstone projects, remember, you don't need to put those legal checked. Okay? Basically, is your experimental design kosher? Okay? Those verifications need to be in the legal need to be in the appendix. So in other words, is that you only need to show that, hey, I have significance, my ANOVA is good, to do multiple comparison. But then when I said your ANOVA is good, how did you know your ANOVA is really good? Couple of things we need to check to say that your experiment run in a legal way. Okay, so before we call it a day. Let me ask you, what kind of legal test you think is important? What is the step one when we run a single experiment? Simple experiment. Remember, I have 4 observations. I have 16 value. Right? I have treatment 1 or treatment A, subway station A, subway station B, subway station C, subway station D, subway station C. What is the first step we do when we run that experiment?
Randomize the order.
Randomize the order. So here is the tricks, okay? So when we randomize the order, why we randomize the order? Remember the argument? Why we randomize the order?
For fairness.
For fairness. So in other words, is that why I should be the last one? Why should he or she be the first one? Right? And so when we do the rank, we have the number, right? So here is the situation, is that once you have the rank of each one of the observation, I can write down in your some books they call it run. Who is the first one and who is the second one? Okay, so the second one in the experiment. Okay, remember, all those numbers could be here, could be here, could be here, right? Could be in a factorial design, could be from low, low, high, high, could be from anywhere. Our last experiment, we have 18 number, right? 3 by 3 twice. Could be anywhere. So it's completely randomized. But if I argue that I am completely randomized, how are you going to prove that? You know? So in other words, is that you run your experiment, you say, Dr. Xiang, Simon, I did it perfectly. I randomized the whole things. And I said, I don't believe you. I think you cooked your number. You cheated. How can you say that, well, here's a piece of evidence to say that I actually run these things in a legal way? How many of you ever heard autocorrelation? Yeah? What's autocorrelation? Autocorrelation means that, okay, how many of you ever read Mark Twain? Never? Okay, when you read Mark Twain said about history, what did he say about history? History never repeats itself, it just rhymes, right? So there is a rhythm in the history. So here, we need to do a rhyme test, okay? Or autocorrelation test. So let me just pretend I have a set of number here, okay? But let me do that. Okay, let me fake a sequence of observation here. Okay, and now I have the observation done. Say that's the sequence of my 25 observation. Okay, and based on this is run 1, run 2, run 3, run 4. Okay, so people, look at the if I'm just doing a plot of this 25 number, okay, do you think they're random or they're not random? Why they're not random? Do you see the magnitude seems kind of increase? Okay, so in other words is that I could be big if my past is big. I could be small if my past is small. Then whenever that happens, means what? History never repeats itself, but it just rhymes. Whatever, where I am right now, it's not completely random. Depends on where I was before, right? If you take 5302, they probably talk about random walk, right? So the first things in our mind is, hey, when you said you completely randomized the whole things, how are we going to check that? I'm going to show you computationally. Okay? So do you think that's a problem? We need to check. Or to have a piece of evidence to say that my experiment is legal for multiple comparison or for factorial design. What will be the next things you need to check? Other than check the clock, see if time to go. Nothing? What else do you need to check? I sometimes have the urge to ask you to write a thesis, a 100 words to say that I guarantee you for the rest of my career, I would never use experimental design. I don't care. Okay. Anybody can tell me what else we need to check? Here, when we have the multiple treatment, we said that the central station and the subway station make the difference. The local commute should be what? Random number, right? Should be a set of random number. So in other words, is that the variation here, and the variation here, and the variation here, the local variation should be what? Pretty much like from a same normal distribution, right? And that assumption is called Iid assumption. Iid stands for independent and identical. Okay? It's pulling out from the same set of random number. So again, I need to check, make sure that every number you get, it's random. And another thing we need to check, okay, is we want to make sure that this things is not, scale. Remember Monday, I talked about when we're going to take log. Sometimes we need to take log of your observations before we run the ANOVA table. I said there are three things motivate us to use log. What are the three things?
So one is if the data has an exponential trend.
Exponential trend, so we need to linearize it. Second one?
There was linearizing and there was one standardized?
That means what? The variations is different category or different block. So sometimes we call it trumpet shape. Sometimes small, sometimes big. Then you need to take that. So we need to take care of that problem and check if the variations here. If I said that roughly speaking, in subway station A, the local commute, okay, mean is 0, the standard deviation is 2. People travel locally for 2 miles or 2 minutes. For subway station 3, B is at 0, but the standard deviation is 4. What do you think the subway station B people will say? It's not fair, right? Why in subway station A, their local commute only a tiny bit? And we want to use the subway, we need to travel a lot more. So we need to have consistent variation station by station, or treatment by treatment. Even for the 9 by 9, 3 by 3, I don't care the cell we have is in here. Back to this one. Okay? If, okay, I have 9 different conditions, right? So I can almost treat it like I have 9 subway stations. But if in subway station 2-1 or 2-2, man, people need to have a lot of local commute. But in some other subway station, hey, it's, one step right next to the subway station. Then that means that inconsistent, okay? Then we need to also consider that that's not legal. And if you insist you have to use it, then you probably need to take log or do something about your data point. So you need to linearize it, okay? And then finally, okay, remember I said you would need to take log, is that when you need to take log? When your observation, the increment, is proportional to your scale. D log x equal to dx over x. Whenever that happens, we need to do something about it. Okay, so next week I will spend probably the first hour of lecture to go through all the computation. But do you guys see why we need to do that now? Basically, I can say that, hey, we've done our experimental design. Everything's under the sun. I can do a 2-way factorial or 3-way factorial or combo. And then do the multiple comparison, figure out the effects, figure out the ANOVA table. And then I'll show you how to do multiple comparison. But then we need to have a legal document to say that's true. Those, I consider for your exam 2. Then exam 3, I basically said, okay, but the world is not just a bunch of square. It's, who knows what shape. So no matter what shape you're dealing with, I can treat them as what? Square by square. Okay? So after we've done everything for exam 2, I will say exam 3, response surface, you can consider it's square dance. How many of you ever been to ballroom dancing? Ballroom? International standard ballroom? Waltz, tango. Never heard? Okay. You can consider I have a palace, for square dance. So there are square by square. Okay? And then the ceiling could be convex, could be concave, could be a who knows what shape. Okay? There could be local optimum, so there are more than one minimum or more than one maximum. You guys follow me? Here, do I still have time?
Got about 5 minutes.
Okay, let me struggle a little bit. Okay, I'll show a local minimum. Okay, so yeah, I will use this. Okay, so there are local minimum, there are global minimum. So the ceiling, okay, got a very, very low point, but it's not so low point. So you can consider square dance as what? I'm doing this step by step, every step looking for the contrast, everything's figured out. Okay, should I move to the right, to the left? And once I move to the right, to the left, I get a little closer. Say I'm coming this way. And get smaller, smaller. I reach a minimum point. But then you want to know, am I reaching a local minimum or a global minimum? Say I'm looking for a real global minimum. Means the ceiling showing that there's something even better. The global minimum somewhere out there. So I need to square dance, not get trapped at the local minimum until I can get into the global minimum. So in order to do this means what? I'm doing a 2 by 2 by 2 with a center point or stretching point, kind of like the combo of 2 and 3, factorial design. Square dance, look at the ceiling, and I'm reaching a better point. Square dance, reaching a better point until I'm reaching the global minimum. And when you do that, are you doing what? A bunch of simple, small experimental design for factorial to figure out which way to go, right? Whenever you've done your previous experiment step by step, you have a lot of value to know which way getting smaller or getting big, right? Even, say you don't know which way is big, which way is small. I plug in all the number, you can always say that which one is the big one, which one is the small one, right? And find the optimum point, okay? So, exam 2 prepare us to do exam 3 for this one, okay? And after we've done that, I can say that, hey, give me any trouble under the sun, at least I have this approach to find the solutions. Okay, see you next time.